Welcome to G Fun Facts Online. Today we're diving deep into a question that sounds deceptively simple. What happens when it rains on the ocean? The obvious answer, the one that oceanographers believed for decades, is that the light, fresh rainwater simply floats on top of the dense, salty sea, creating a calm, stable layer. It makes perfect sense. But as we so often find in science, the most obvious answer is rarely the whole story. The reality is a chaotic, turbulent battle of physics, where the gentle patter of raindrops can, under the right conditions, churn the ocean surface more violently than a torrential downpour. This isn't just a neat party trick of physics. It's a fundamental process that dictates how the ocean breathes, how it feeds the microscopic life at the base of the food web, and even how it fuels the most powerful storms on Earth. So let's explore the unsettling influence of a gentle rain. At the heart of this entire process is a fundamental conflict, a duel between two opposing forces. One force wants to create order and stability, neatly separating the ocean into layers. The other wants to create chaos and mixing. The winner of this duel shapes the very surface of our planet. Let's start with the force for stability, buoyancy. This is the intuitive part. Rainwater is fresh water, meaning it has a salinity of virtually zero. Ocean water, on the other hand, averages a salinity of about 35 parts per thousand. All that dissolved salt makes seawater significantly heavier and denser than fresh water. So when rain falls, this less dense fresh water naturally wants to accumulate at the surface. It forms a distinct, buoyant layer that resists mixing with the heavier, saltier water just inches below. Oceanographers call this a freshwater lens. These lenses can be surprisingly persistent, lasting for hours or even days, and can stretch across vast areas of the open ocean. When this rain-induced layer is particularly strong, and it forms within the upper part of the ocean that has a relatively uniform temperature, it creates something called a barrier layer. This name is very literal. The layer acts as a physical barrier. It traps heat from the sun, momentum from the wind, and gases like carbon dioxide in a very shallow surface layer. It also prevents the cooler, often nutrient-rich water from the deep from being mixed upwards. This effect is especially pronounced in tropical regions with high rainfall, like the Western Pacific, where these barrier layers are a semi-permanent feature of the ocean. So on one side of our duel we have buoyancy, driven by salinity differences, working hard to create a stable, stratified ocean surface. But on the other side we have the agents of chaos, working to tear that stability apart. These agents come in two forms: the physical punch of the raindrops and the thermal shock they deliver. First, let's talk about kinetic energy. Raindrops don't just gently merge with the sea. They hit it. Each drop, no matter how small, strikes the surface with force, transferring its kinetic energy and creating turbulence. If you could zoom in, you'd see a chaotic mess of crown-like splashes, tiny ring waves, and swirling subsurface eddies. This is rain-induced turbulence. Now, here's a fascinating detail from laboratory experiments. A surprisingly tiny fraction of the raindrop's kinetic energy, only about 0.1 to 0.3%, is actually converted into this mixing turbulence. Yet, even this tiny amount is often enough to drive significant mixing in the top few centimeters or inches of the water column. The size of the raindrops is critical here. Big, heavy drops, like the ones in a tropical thunderstorm, carry much more momentum. They punch through the surface and can cause substantial mixing. Smaller, lighter drops, like in a drizzle, are more likely to be overcome by the forces of buoyancy, helping to create that stable surface layer. So the physical impact of rain is a powerful force for mixing, but it has a partner: thermal shock. Rain isn't just fresher than the ocean, it's almost always colder. Raindrops form high up in the atmosphere where it's cold. By the time they reach the sun-warmed surface of a tropical ocean, there's a significant temperature difference. Furthermore, the big convective weather systems that produce rain are often accompanied by what are called cold pools. These are pockets of cold, dry air that are dragged down by the rain itself. They hit the ocean and spread out like a pancake, dramatically increasing the rate at which heat is pulled from the water into the air. This combined cooling effect from the cold drops and the cold air has a crucial consequence. It increases the density of the very, very top layer of the ocean water. Cold water is denser than warm water. If this cooling effect is strong enough, it can make that razor-thin surface layer heavier than the slightly warmer water just beneath it. And what does heavier fluid do when it's on top of lighter fluid? It sinks. This triggers a process called convection, a vertical mixing that actively destabilizes the water column. So we have this epic duel, the stabilizing power of freshwater buoyancy versus the destabilizing chaos of kinetic energy and thermal cooling. The big question is, who wins? For a long time, the thinking was that stabilization almost always won. But groundbreaking recent research has revealed that the outcome depends on a delicate balance, and the single most crucial factor is the rain rate, how hard it's raining. And the result is completely counterintuitive. Let's look at light rain first. We're talking about rates between approximately 0.2 and 4 millimeters per hour, a steady drizzle, not a downpour. In this scenario, the amount of fresh water being added is modest. The freshening effect isn't very strong. Here, the cooling effect from the raindrops and their associated cold pools often dominates the equation. The surface water loses heat, becomes denser, and sinks. The mixing caused by this thermal shock is stronger than the stabilizing effect of the added fresh water. The net result is that light rain actively destabilizes the ocean surface, promoting mixing. Now, let's crank up the intensity to a heavy downpour, anything greater than about 4 millimeters per hour. Here, the sheer volume of fresh water being dumped onto the surface is immense. This massive input of low salinity, buoyant water creates a very strong stratification of very powerful freshwater lens. The cooling effect is still happening, but it's completely overwhelmed by the stabilizing power of all that new fresh water. The result is a net negative buoyancy flux, which is a technical way of saying the ocean becomes highly stable. So let's be clear on this amazing paradox. A light, gentle rain is more likely to mix and churn the ocean surface than a heavy, violent downpour. Of course, rain rate isn't the only factor. Wind speed and even the time of day play a crucial role. Wind is the undisputed king of ocean surface mixing. At low wind speeds, the subtle effects of rain, both the kinetic impact and the thermal cooling, can really shine. But as wind speed increases, the powerful shearing force of the wind begins to dominate all other factors. A strong wind can completely erase a rain-formed freshwater lens in a short amount of time, mixing it deep into the water column. Then there's the difference between night and day. Studies have found that nighttime rain is twice as likely to cause instability as daytime rain, even at the exact same intensity. The reason is simple: sunlight. During the day, incoming solar radiation is constantly warming the ocean surface. This warming helps to counteract the cooling effect of the rain. But at night, the ocean is losing heat to the atmosphere. Without the sun's warmth, the cooling effect of the cold raindrops is much more potent, making destabilization and mixing far more likely to occur. But even when a heavy downpour creates what looks like a perfectly stable, impenetrable barrier layer, the ocean has another trick up its sleeve. A more subtle, almost ghostly form of mixing can occur through a process known as double diffusion. This is one of the most elegant concepts in fluid dynamics. It happens when a fluid has two different properties, in this case salt and heat, that both affect its density but diffuse or spread out at very different rates. In water, heat diffuses about 100 times faster than salt. So imagine the situation we have: a layer of cool, fresh rainwater sitting on top of warmer, saltier seawater. The conditions are perfect for a specific type of double diffusion called diffusive convection. Here's how it works, step by step. First, At the sharp interface between the two layers, the warmer, saltier water below begins to transfer heat upward into the cool, fresh layer above it. Because heat diffuses so quickly, a thin slice of the seawater right at the interface cools down. It has lost its heat, but it hasn't lost its salt. This now cooler, still salty water is suddenly much denser than the warm, salty water below it, and so it begins to sink in thin plumes. At the same time, the thin slice of rainwater just above the interface is soaking up that heat. It warms up. This now warmer fresh water is significantly lighter than the cool rainwater above it, so it begins to rise. What you get is a chain reaction. Convection starts happening on both sides of the interface, driven by the rapid transfer of heat. This process mixes heat and salt across the boundary much more effectively than simple diffusion ever could. Over time, this can lead to the formation of a thermohaline staircase, a series of distinct, well-mixed layers stacked on top of each other. It's a telltale sign that this subtle but powerful mixing engine is at work, secretly breaking down the very barrier that the heavy rain created. So this intricate battle between stability and instability, this secret mixing by double diffusion, why does it matter? The consequences are truly global, affecting everything from the air we breathe to the food we eat. Let's start with life in the ocean. The structure of the surface layer is the master control on marine productivity. The sunlit upper layer of the ocean, the euphotic zone, is where phytoplankton live. These are the microscopic plants that form the absolute base of the entire marine food web. Through photosynthesis, they produce about half of the oxygen on our planet. To grow, they need two things: sunlight, which is plentiful at the surface, and nutrients like nitrates and phosphates. The problem is, these nutrients are often more abundant in deeper, cooler waters. So a rain-induced destabilization event, whether it's from the thermal shock of a light rain or the kinetic punch of large drops, acts like a giant spoon. It stirs the pot. This mixing can dredge up those vital nutrients from below, injecting them into the sunlit zone. This is a feast for phytoplankton. Studies have shown that rainfall events, especially those associated with major storms like typhoons, can deliver a huge pulse of nutrients, leading to remarkable and rapid increases in phytoplankton biomass. You can literally see the ocean turn green with life from space after one of these events. But the opposite is also true. When heavy rain creates a strong, stable barrier layer, it slams a lid on the system. It traps the phytoplankton in a sun-drenched but nutrient-poor surface layer, effectively starving them by preventing the upward flow of nutrients from the deep. This can crash productivity and completely alter the structure of the local ecosystem. Beyond feeding the oceans, this rain-induced dance directly regulates our global climate. The ocean's surface is the planet's skin. It's the primary interface through which heat and gases, most importantly carbon dioxide, are exchanged between the atmosphere and the ocean. The state of this skin is therefore critical for climate regulation. When a stable barrier layer forms, it traps the sun's heat near the surface. This leads to higher sea surface temperatures, which can influence weather patterns by providing more energy to the atmosphere. This stratification can also act as a lid on gas exchange, slowing down the ocean's ability to absorb the excess carbon dioxide we're pumping into the atmosphere. But when light rain destabilizes the surface and creates turbulence, it roughens the skin and enhances the gas transfer. Cooler water can also hold more dissolved gas. So a cooling rain event can temporarily flip a region of the ocean from being a source of CO2 to the atmosphere into a sink for CO2, actively drawing it down. This has direct implications for our global carbon budget. Perhaps the most dramatic consequence of all is the link to hurricane intensification. Hurricanes are heat engines, fueled by the thermal energy stored in the ocean's upper layers. The formation of those rain-induced barrier layers we talked about can be incredibly dangerous. By trapping solar energy in a very shallow layer, they can create patches of unusually warm sea surface temperatures. These warm patches are high-octane fuel for tropical cyclones. A developing storm that passes over one of these pre-existing hotspots can undergo what's known as rapid intensification, a sudden and often unpredictable explosion in wind speed and power. The state of the ocean surface, which is directly influenced by previous rainfall patterns, plays a critical role in setting the stage for a storm to transform from a manageable system into a catastrophic monster. In the end, the simple act of rain falling on the sea is anything but simple. It's a complex cascade of physics that challenges our intuition. It's a world where a gentle rain can be a more potent mixer than a raging storm, and a calm, stable surface can hide the subtle but powerful engine of double diffusion. Understanding this process is fundamental to understanding our planet. It reveals the intricate connections between a single raindrop and the global climate, the microscopic life that supports the oceans, and the awesome power of a hurricane. It's a beautiful reminder that in the natural world, even the most gentle forces can have the most profound and unsettling influence. Thank you for listening to Fun Facts Online.